me make sure I'm recording because I lost one last time. Okay. All right, so here we are. We're coming towards the end of the course. By the way, the midterm grades are up in Canvas. You should be able to see them there. I hope there are no surprises. I think there were a couple of people who had points on the automated scoreboard with a fake name, and I couldn't figure out their real name. So take a look at your midterm grade, and if something's wrong with it, let me know so I can fix it before we get to the final grades. Anyway, we're going to talk about Windows Overflow and do some demonstrations here. So here's some more Windows Overflows. We'll do stack protection, heap overflows, and some others. So there are some defenses that protect you from stack overflows. Now here's a project we did a while ago where you have a pin. You ask for a password, and then you'll get fail if it returns 1. Now in this case, this is an early one I wrote. There actually is some combination of bits that will be considered correct, but it's not easy to figure out. And of course, the better way to solve it is to perform a buffer overflow. But the interesting issue is when you compile it with and without a stack protector, then you'll get different sizes. So if you compile it with a stack protector, that's the one called PWDP, and that one is a little bit bigger. This one is 15,540, this one 15,628. So it adds 100 odd, or it looks like maybe 80 more bytes to it. But this makes it a little bit safer. And what it's done, if you disassemble it, you can see it has added this code in the prologue. Now here's the prologue. When you enter the function that's going to have the buffer overflow, you create a stack frame by pushing EBP and moving current EBP into ESP, then subtracting 24 from ESP to make room for 24 in hex bytes of local variables. And then here's the special part. You now move something from a GS address. GS is a segment register pointing to wherever they apparently store the pseudo-random value used as a stack protector. They move it here, and so it's going to copy a value to the bottom of the stack frame. So it's going to put it on a location related to the EBP. And the point of this is you have your local variables stored, and then it puts a special flag value at the end of all your local variables, but before the stack pointer. And now if there's an overflow, it will notice that that value has changed. If you go to the end of the function, instead of just returning, before it returns, it retrieves that value stored at EBP plus 12 and compares it to the stored value in this location addressed by the GS stack segment register. And there it's able to tell if the stack check fails. This is the security. We took a few lines of assembly code at the start and end of each function that's protected in this manner, and it makes it impossible to do the kind of buffer overflow we've been doing, where you overflow a local variable and you overwrite a whole bunch of bytes in the whole stack frame until you hit the return pointer. If you do that, it will fail the test here, and the function will not return. It will not use the corrupted value you put in the stored return pointer. All right, so that's a stack protector in Linux. You have the same thing in Windows, you can see it here. When you make the same function in Windows and then just compile it, you can compile it. EHSC is some kind of default stuff that does normal compiling. GS minus does it without a stack protector. So the N has no stack protector. So if you compare it, you see the PWDN is a little bit shorter. Looks like 500 bytes shorter. It's the same thing. Everything is, of course, bigger and less efficient in Windows. That's Windows for you. That's why people like Linux. Linux is small and compact and efficient. Windows is big and bloated and complicated. All right, and if you can disassemble it with IDA-free, and you'll see here's the stack prologue in the one without the protector, and here's the stack prologue with the one with the protector, and you can see it gets something called security cookie and manipulates it. It's going to manipulate it at the entrance and exit of the function the same way. That's the same kind of thing. All right, so that's stack protection. So that's the GS compiler flag puts a security cookie, which is Microsoft's word for what Linux calls a canary, an extra random value just stored on the stack to sit there and at the end of the function be checked to make sure that it has not been modified to block buffer overflows. All right. Now, this would have to be a random, unpredictable value. If it was always the same, you could carefully craft your buffer overflow to put the expected value there. So Here's how it looks. You have your variables stored here. Then you have the security cookie here before the saved EBP and the saved return address. So you can't hit these important control flow parameters. All you can do is leak from one variable into another, which means you can do some versions of buffer overflow, but you can't do the kind that directly gives you control of the instruction pointer. So now you have to make this semi-random cookie. So what Microsoft does is try to make a effectively random number. They take a time, process ID, thread ID, another time, and a performance counter, and try to XOR them all together to try to make a number that is effectively random. And if you could predict it, especially if you can run local malware on the system to get the information to predict it, then you might be able to predict some of the bits. And so there were people that tested this, and they found that in practice they were able to predict a lot of the bits. So instead of having 32 bits of randomness, it really only had 17 bits of randomness in practice in Microsoft Windows. So that means there's about 100,000 possible values of the stack cookie. So if you could run an attack 100,000 times or 200,000 times, you'd have a pretty good chance of guessing the cookie. All right, so we talked about this. The other thing you could do, of course, maybe you could modify the prologue, or maybe there's modifications that it makes. It adds, like say, handling a security cookie at the entrance and exit of the function, the same as Linux does. That's how it works. So the security check cookie is stored in ECX and compared to an authoritative value. If it fails, it's going to go and report the failure, stop your program, and pop up an error message. All right, so before this flag, local variables were placed in the order of their declaration. Now all the arrays are moved to the bottom of the list, so this makes it harder to overflow an array and hit other values. So this is to stop the other kind of buffer overflow I mentioned, where one variable overflows into another without hitting the cookie or the return value. That can also be bad, but by putting all the arrays at the end, you limit the number of variables that are after an array. All right, so here, if you put these at the start, then I can hit these things like isAdmin, but if you rearrange them so all the non-array variables are at the start, then I have less to hit with these. All I can do is hit other arrays, which might have some effect, but it's less likely to be control parameters. All right, that's just a picture of the same thing. All right, so we changed the cookie, but a parameter is used in the right operation, right. So you could, the parameter you could have effect by changing a value of another parameter. You could end up doing something unexpected. All right, then you can do it all on the heap instead of the stack. Remember, the heap is for a program that uses a lot of data temporarily. So if you're, for example, take network data like a web server, you take a request, you want to store it, process it, answer it, and then you're done with it. You want to use that memory over again for the next request. That's what you do with the heap. You reserve space on the heap, you use it, then you free the space on the heap so you can keep running without having to consume a lot of extra memory. That's the game. So each process has a heap, and you can get a pointer to it. And so this is the code that returns that pointer. And this is the default process heap used by the API. You can also make dynamic heaps if you want to. You can break the heap into subheaps and use them separately. Some coders do that. So you'd have the default heap, and then you have other heaps down here. And the process environment block pointing to the default heap. So you can allocate the heap, and when it's done, you call heap free, or there are other free functions. All right, so the stack goes downward, the heap goes upward, and it starts with a list of entry structures to keep track of free blocks. And we talked about this before. If you have 3 blocks in a row in the heap, each one of them stores some data, and each one of them has a forward and backward pointer pointing to the next block chunk of data on the heap and the previous chunk of data on the heap. But when you delete the one in the middle, it has to update the forward pointer from this one to skip over, and the backward pointer from this one to skip over. And if you had been able to overflow this data, you're going to end up writing to an address which is under the control of the attacker, and the data is also going to be under the control of the attacker. So you don't get to control the EIP, but you do get to control a write operation which you can use to write to an address location that will eventually go into the EIP. So the end result is it can be as powerful as a Stack Overflow. All right, and it is pretty complicated on Windows. They have a lot of other features in Windows that are not present in the simple heaps used in Linux. So there's 3 ways to exploit it. You can override a pointer to an exception handler and then cause an exception. You can go to the unhandled exception filter or go to the PEB, process environment block. These are some ways to exploit a heap overflow. All right. And this would be a pointer that's called whenever you exit process, and that's a location is fixed in versions of Windows NT, so that's a thing to know about. And that's the point. Remember, in Linux, we found some pointers to libc. We were able to override a pointer to a C function like exit. So when you try to call exit, you're actually calling a function under attack or control. So Windows 2003 server had some functions that could be controlled. And there's something Windows XP brought up called vectored exception handling. All right. And that stores information about handlers on the heap where a heap overflow can hit them. And this is something been around for about 20 years now, maybe 25 years now, a way to override a pointer to the unhandled exception filter. Now, we talked about this. You can write code to handle exceptions, and if they fail, then it goes to be an unhandled exception, and it goes to the operating system that will pop up a generic message like your program has crashed. All right, so the overflow corrupts the heap, and the simplest repair process is to just make the heap look fresh and empty with the only the one block we've added to it. This is one way to make the heap stop being invalid. You can restore the exception handler that you abused. That's a problem, overflowing the heap. You may want to limit your collateral damage if you don't want the program you've exploited to crash. And there are COM object models. We mentioned them before. These things are sort of like services. They're pieces of code that can be reused. And it's created when needed, like a library that's loaded into memory when needed. It has methods and attributes, and they're created on the heap. So they have interfaces that connect to something called a vtable with pointers to the methods available, and they contain data. And the data can be arrays, and the arrays can overflow. So you can have buffer overflows inside the COM objects on the heap. And there turn out to be an awful lot of these because a lot of these COM objects are very old, and Microsoft programmers didn't even know what a buffer overflow was until after they wrote Windows XP. So many coders didn't know at that time. So the older software, it tends to be very vulnerable. So they have a kill bit list with over 600 entries, which are known vulnerable COM objects that shouldn't be used. And you can view it with a tool here, a tool called Olay COM Object Viewer. You can view the COM objects available on your Windows system, and there are a lot of them available, just like there are a lot of services and a lot of libraries. And it turns out, by the way, there are ways to exploit them. One simple way is you can override that kill bit. There are a lot of vulnerabilities in the COM system. And there are other things you can overflow. You could overflow the data section of your program. If you store a buffer here and then have more data later, you might be able to overwrite this and change the pointers. This would be just one variable leaking into another, like we said before. And there are, in principle, buffers in the thread environment block, which could be overflowed changing pointers, although there are no public examples of people succeeding in taking over the box with that kind of exploit. So, anyway, there's a quick overview of a few more kinds of overflows that are out there. Let's try Kahoot. Oh, I should move this so you can see the whole number. I guess that is the whole number, 169, okay. So which defense is also called a canary? Yeah, security cookie is another term for it. All right, what does Windows API functions use? They use the process heap. The default heap is what they use. All right. All right. Which item is added to a kill bit list when you find defects? That is Microsoft's security measure for this. Yep, those are COM objects. They have a kill bit. I think ActiveX objects also have a kill bit list. All right, which API call is most likely to be exploited by heap overflow? Yeah, we talked about this before. It's freeing a chunk that leads to an arbitrary write operation if there's been an overflow. All right. And which item is created when needed by another program? COM objects are loaded into memory like libraries. They're created as needed. Otherwise, they just rest, I think, as inert files on a disk. But you create them when you need them. All right. Let me stop this one.